Hello everyone, welcome to Chapter 4, Applications of Derivatives. The focus here would be on the mean value theorem, and this is a central theorem in calculus. It is fundamental to the idea of derivatives. And so we'll look at this theorem, and in order to understand, appreciate, and even be able to prove this theorem, we will begin with Rolle's theorem. Let's look at the definition of Rolle's theorem. Rolle's theorem states that suppose y equals f of x is continuous over the closed interval ab and differentiable at every point of its interior ab, and if f of a equals f of b, then there is at least one number c in ab at which f prime of c is 0. Let's look at the premise first. Y equals f of x must be continuous. The function must be continuous over the closed interval ab and differentiable within ab at every point. This makes sense because we remember that differentiability implies continuity. Continuity need not imply differentiability. Therefore, the emphasis here is that f of x must be continuous, but it must also be differentiable in the interior of AD. Because if we were looking at the endpoints a and b, there is a possibility that you have a one-sided derivative. That means it won't be differentiable. Therefore, they're saying every point in the interior of AB must be differentiable. If these things hold true, and if you can find a particular instance where f of a and f of b are the same, then, meaning they're equal, meaning the endpoints, then there is at least one number. You can find some point within that AB where its derivative would be 0. So it's well illustrated here in these two examples. So in the first graph, you see that A, B are the endpoints, and it is a closed interval because you have the solid dot at A and B. And you're looking only at the piece of the graph that is between A and B. So this graph, you can see, is smooth and it's continuous. If it was pointed, it would still be continuous, but if it's pointed, then it wouldn't be differentiable at every point, right? So here, this is a smooth curve, and therefore we know it is differentiable at every point in the interior of AB. And as we can see, there is a point where it reaches a peak and then falls back. And that point C, correspondingly, on the graph, will have a horizontal tangent, because that is how you find the slope, isn't it? So the slope for any horizontal line is 0. So horizontal tangent at C on the curve is 0 in this case. And that is what Rolle's theorem assures or guarantees. Now, what if your graph looks a little differently with more turns? Well, again, look at the second graph between A and B. You have all these turns. And Rolle's theorem assures that there will be at least one number C at which the slope will be 0, or the derivative, right? The first derivative is 0. In this case, we have, because of the number of turns, we have actually 3 points, 3 places where you have a horizontal tangent. And this kind of helps you to recall the first derivative test as well, right? The first derivative test said if there is a local maximum or local minimum, then f prime of c at those points will be 0. And in fact, you can see that this is a local maximum C1, and there is a local minimum at C2, and there's a local maximum at C3. But you also know that you can find the absolute, in this interval A to B, absolute minimum is C2 and absolute maximum is C3, because among all the minimum, or minima, I should say, this is the only one. In fact, there was only one minimum value, so that's there. Among all the maxima, you have one that is the maximum, absolutely, and that is here C3. Anyway, so we can see a lot of other things that we've learned before coming together. Okay, so Rolle's theorem really is very intuitive, and you can kind of understand that very clearly, that this is a possibility that you'll find at least one value where the derivative is 0. We're going to use this idea to prove or to kind of lead into the mean value theorem. So I have here these 3 graphs, and we're going to use this to see if we understood the premise of Rolle's theorem and if the hypothesis of Rolle's theorem holds or not. So let's take a look at the first graph. Okay, we are told that f of x must be continuous on the closed interval AB. Okay, right there, that information is missing. So even though f of a is equal to f of b, right? So they carry the same corresponding y value, it really doesn't hold true here. So I'll just say discontinuous at an endpoint. Because on the left end, the A is discontinuous. So Rolle's theorem really does not hold true here. You cannot find a value in between them, between A and B, or in the interior of A and B, where f prime of that particular value is 0. Let's come over here. Here, y equals f of x. In the second graph, you see again a disconnect there, right? So A and B, at those endpoints, there is continuity, but there's a discontinuity in the interior. So I'll say discontinuous at an interior point. In fact, you know, the point where it's disconnecting is x naught. So on the interior point of AB. Okay, so that's again where it fails. Then let's go to the third one. Okay, so AB, is this a continuous graph? Yes, there are no breaks, no jumps, nothing. It's a continuous graph. Y equals f of x is continuous. And the Rolle's theorem goes on to say it should be continuous on the closed interval AB. That's also true. And it should be differentiable at every point in the interior of AB. So is it differentiable everywhere? You see a corner, a pointed part of the graph. And right there, you know that it's not differentiable. So Rolle's theorem does not hold true here as well. So I'll say continuous on AB, but not differentiable at an interior point. In this case, the point is x naught on A. So this is just to help us understand that whenever we say theorem, as I mentioned before, we want to always consider the premise first. If the premise is satisfied, then the theorem's guarantee will work. Okay. Now let's take a look at the mean value theorem. This was first stated by Joseph Louis Lagrange, and what I find really clever about this is that mean value theorem is just a slanted version of the Rolle's theorem. Rolle's theorem keeps it all horizontal, right? So it says if f of A is equal to f of B, which means it should be a horizontal line. You can actually look at that, right? See here, f of A equals f of B. And here too, this yellow line, f of A equals f of B. And then if that is true, if f of A equals f of B, then you can find at least one C where f prime of C is 0. Yeah. Now this idea, if you took it as a slanted version, then you won't have f of A equals f of B, right? Because when it's slanted, when it's off, it's not a horizontal line, it will be a slanted line. Therefore, they will have different f of A and f of B values. So what happens here is that the mean value theorem says, suppose y equals f of x is continuous over a closed interval AB and differentiable on the interval's interior, then there is at least one point C at which the slope of the secant line is the same as the derivative at that point. That's basically what they're saying. Okay. In other words, the mean value theorem, the shortcut for that is MVT. Remember, EVT was extreme value theorem. This is mean value theorem. MVT's guarantees that there is a point where the tangent line, right? Look at this red line. This tangent line is parallel to the secant line joining any 2 points on the curve A and B, particularly the endpoints A and B. So if you were to find the slope of the secant line, right, that will be you'll find another point where the tangent line is parallel to this secant line. So this is the secant line. So when they say chord, that chord is your secant line. Okay. So here we have this graph between A and B, closed interval, y equals f of x is a continuous graph, so it is smooth. Instead of looking at a horizontal information, we're looking at the endpoints where f of a is not equal to f of b, but you can connect a and b as a secant line and find its slope. Slope of a secant line is a regular slope formula, right? y2 minus y1 over x2 minus x1. Here, y2 is f of b, and this is f of a. So f of b minus f of a over b minus a. That is your slope, and that will be equal to the slope of the tangent line. And why will that be equal to each other? That's because that's the property of parallel lines, right? Parallel lines have the same slope. Parallel lines have the same slope. This is a property we learned in algebra, and that's a property that helps us to prove this MVT. So this implies that the slope of, I'll just write here, slope of the secant line, right, AB, is the same as the slope of the tangent line because they are parallel. Therefore, f of b minus f of a over b minus a is the same as the slope of the tangent line, which is f prime at c, and they're equal. Now, the Rolle's theorem says that the slope will be 0. They gave an exact value just because it was a horizontal tangent. But here it is a parallel one. It's not horizontal. Therefore, there will be some value to this. It will be a numerical value that you can find that is not 0. Now, I'd like to illustrate the MVT idea here. Let's consider y equals x squared. And it's between, of course, 0 and 2. Let's say that's the interval between 0 and 2. It is a continuous function in a closed interval AB, which in this case is 0 and 2, 0 to 2. And it's differentiable at every point in the interior of 0 to 2. So then I'll just say continuous and 0 to 2, it is differentiable. Now notice I wrote 0 to 2 with the open parentheses on both ends to indicate that it's the interior of that closed interval that needs to be differentiable. So this is a symbolic notation of putting that in words. Okay. All right. So what does MVT tell us? MVT says, well, if you took the slope of the secant line, then you can find a point in between 0 to 2 where the slope, we'll find at least one point where its slope will match with the slope of this red line. Okay. So the slope of the secant line is between 0 and 2, isn't it? So that will be f of 2 minus f of 0 over 2 minus 0, right? But we know that this coordinate is 0, 0, and this coordinate will be 2, 4, because when you plug in 2 in your y equals x squared, 2 squared is 4, so you know that. And so I'm going to just use that 4 minus 0 over 2 minus 0. So the slope here is 4 over 2, which is 2 here. Now we don't know, now in this case we kind of see where it's happening, where you can find the corresponding line that's parallel to it. But if we didn't know what the tangent line would be, we can simply find the slope of the tangent line to be f prime of x, right? And we need to find at some value c, where x equals c. So what is f prime of x? We know f of x is x squared, right? Y equals x squared. F of x is x squared. So take the derivative of x squared, that gives us 2x, where x is that particular value c. 2x is for the entire function. This is for a particular value c, which means it's 2c. So MVT allows us to find what that value is. So set the secant line, the slope of the secant line equal to the slope of the tangent line, and you get c equals 1. So if you come back here, it is here at 1, 1 that you find that the slope is matching with so there is at least one point where that slope matches with the slope of the secant line. So MVT guarantees that, and therefore it helps us to even find that particular missing point, unknown point, not missing, unknown point. Sometimes it's not always easy to find it like this, algebraically, but we know that it always exists. And so that is the guarantee that you get from MVT. I'll also illustrate using another real-world example. Let's take a look at this example. If a car accelerating from 0, okay, look at the graph here. I'm going to explain this using the graph down here. The car is accelerating from 0, takes 8 seconds, okay, so that's your t. So it takes 8 seconds, 5, 6, 7, 8. 8 seconds to go to 352 feet. Okay, that's the corresponding y value here. So from 0, it accelerates and gets to 352 feet in 8 seconds. Its average velocity for the 8-second interval, right? This 8-second interval is 352 divided by 8. Okay? Well, that's 352 minus 0 over 8 minus 0, because this is 0, 0. Okay? But you can see that the average would be 352 over 8. You can see it that way too, which is 44 feet per second. The mean value theorem says that at some point during the acceleration, the speedometer must read exactly 44 feet per second. In other words, 30 miles per hour. So what we're saying is, you can think of this as any other regular example, right? For instance, let's say you are driving from Merced to Los Baños. So the let's say the posted speed limit is say 40 miles per hour. Okay, so you're not going to drive exactly 40 miles per hour. You go up or down, isn't it? So if there is heavy traffic, you probably were driving at 30 miles per hour. If the road was fairly clear, you were probably driving at 42 or 45 miles per hour. What happens is you either speed up or slow down depending on the traffic. But what we're saying is, on an average, let's say you were driving at 42 miles per hour. At some point, you went down to 42 or you went up to 45, but you were maintaining that a certain speed, but at some point you were exactly at 40 miles per hour, right, at the posted limit. At some point you were there. So that is what this means, that the MVT guarantees that your speedometer must have read that value exactly, that 40 miles per hour speed limit, because you were driving around that limit, right? So we have two corollaries that come as a result of Rolle's theorem and mean value theorem. A corollary is like a byproduct, an obvious consequence of a theorem, okay? And sometimes it can be, an obvious result that this theorem could lead to. So corollaries are kind of offshoots of a theorem, right? So corollary 1 is an offshoot of Rolle's theorem, and corollary 2 is an offshoot of mean value theorem. Corollary 1 says, if f prime of x is 0 at each point x of an open interval, then f of x equals c for all x that belongs to a, b, where c is a constant. Think about this. They're saying f prime of x equals 0 at each point x on an open interval. Every point on x must have a slope that is 0. When can that happen? Think about it. That can happen only when if your graph is like this, okay? Let's say if your graph is going up and down like this, well, you can only have 1 point here and 1 point here. So there are only 2 points between A and B that have horizontal tangent. But we want every point to have it. And the only case that can happen is when it is a horizontal line, so that every point you consider on it, right? Every point has a derivative that is 0. So that is what they're saying. If f prime of x is 0 at every point, let's say between A and let's say this is B, between A and B, then we're saying that is possible only if, in turn, the function f of x was a horizontal line. And what is the definition or the equation of a horizontal line? It's always y equals some number. So f of x equals c is a format to indicate a constant function. A horizontal function is a constant function. So this is the reverse of that, right? So if f prime of x equals 0 at every point, then the obvious consequence of that is that you will have the function to be a constant function, f of x equals c. Okay. Now, corollary 2 states that if f prime of x is equal to g prime of x, like we saw in the mean value theorem, okay, if you have two slopes that are equal coming from two different functions, if the slopes of two different functions are the same, then those two functions must be separated by a constant. Okay. In other words, those two functions must be parallel. Okay. So slopes of two functions equal implies the two functions are parallel. How do we know two lines are parallel? If we want the two lines to be parallel, they'll be separated. They should be a little away, apart from each other, right? And so f of x will be g of x plus some constant. That constant kind of separates them. It moves them, shifts them away from each other. Because if you just had f of x equals g of x, then they will be one and the same line. If you want them to be parallel, they have to be visible. They have to be distinct. And to make them distinct from one another, they have to be separated by a distance by a constant value, some c. And that's what corollary 2 states. Now let's look at some examples. Let's start with checking mean value theorem. So here we will be given a problem and we'll be asked to find the value. So find the value or values, because you could have more than one, of C that satisfy mean value theorem. And the first one is f of x equals x power 2 over 3, and the interval is from 0 to 1. Okay. Again, for mean value theorem, for any theorem for that matter, you want to make sure that the conditions satisfy. So is this continuous? Yes, it is a continuous function. You can always use your graphing calculator to check that. So it is a continuous function on, I was going to say AB, but here you have 0 to 1. Is it differentiable? Again, if you look at the graph of this on your graphing calculator, you will see that it's a smooth graph, so it's differentiable on the interior of 0 to 1. So this implies we could use MVT. MVT implies that f of 1 minus f of 0 over 1 minus 0, the secant line that connects the 0 and the 1 points, will be the same as f prime of c. Okay. So we need to now find these individual values and then we are ready to plug them in. So f of x is x power 2 over 3. This implies f prime of x will be 2 over 3 x power 2 over 3 minus 1. 2 over 3 x power negative 1 over 3. LC. Oh, that's 2 over 3 and x power 1 over 3 in the bottom. Got that side. Now we need to find f of 1. F of 1 will be 1 power 2 over 3, which is 1. F of 0 will be 0 power 2 over 2, which is 0. And then here, f prime of c will be 2 over 3 c power 1 over 3, because you're plugging in for x as c. We got all these values. Now let's go ahead and put it in the MVT. So f of 1 minus f of 0 over 1 minus 0 is equal to 2 over 3 c power 1 over 3. You're setting these two equal to each other. So that's basically 1 equals 2 over 3 c power 1 over 3. And if we solve for c, we will get our values which satisfy the MVT. So 3 c power 1 over 3 equals 2. C power 1 over 3 is 2 over 3. Now I need to get c. I need to solve for c, not without any power on it. The way to undo 1 over 3 is to cube on both sides. See, take the cube on both sides, so that the powers will multiply, and therefore 1 over 3 times 3 will cancel each other. So you get C equals 2 cubed is 8 over 3 cubed, which is 27. So when C is 8 over 27, you will find the slope there at that point, the derivative at that point, will be the same as the slope between 1 and 0 on the, 0 and 1. Slope between the endpoints 0 and 1. I'd like to illustrate this result using the graph. So if you did your graphing calculator for x power 2 over 3, your graph would look like this. You do see a pointed feature here, which means that you cannot have, it's not differentiable at that point. So technically it's a continuous function but not differentiable. However, remember that we are looking at between 0 and 1. So in that interval, this portion of the graph is perfectly fine, right? It is continuous, it is differentiable on the interior of 0 to 1, and therefore this was good for MVT. MVT is guaranteed. And we are told that at this point, so if you connected these two endpoints and you draw a line through them, that secant line, the slope of that line will be the same as the slope of this line, which is at this point 8 over 27, comma, if you plug this in the function, x power 2 over 3, 8 over 27, the whole power 2 over 3 will give you 4 over 9. So if you draw a line, a tangent line through that point, that tangent line and this secant line will be parallel to each other. And that's what I have here. Okay, so if you have the graph like this from just the 0 to 1 portion of x power 2 over 3, if you connected 0 and 1, if you draw a tangent line through this green point, they both will be parallel. Let's do a similar problem with a different function. So here we have f of x given to be x plus 1 over x, and it is from half x plus 1 over x. Again, I want you to go into your graph and learn to use your graph to identify these things. You know, it's a rational function, so it's going to look different, but again, focus only on the closed interval, half to 2, and see if things are good there. And if things are good, which it is, then you'll find that f of 2 minus f of half over 2 minus half will be the same as f prime of c, and we need to find that c, isn't it? So as before, let's go ahead and define f of x and its derivative. That's going to be 1, derivative of x is 1, plus, rewrite this 1 over x as x power negative 1. We've done this before in a previous problem, in a previous lecture. So negative 1 x power negative 2, which is 1 minus 1 over x squared. And then f of 2 will be 2 plus 1 over 3. Again, we can simplify this. F of half will be half plus 1 over half. Now I can simplify that, but I anticipate that when I do the half, this also comes back as half plus 1 over half is 2, isn't it? And so I have that there, and then f prime of c will be 1 minus 1 over c squared. So as per MVT, it implies that 2 plus half, f of 2 minus f of half, all over 2 minus half will be equal to this f prime of c. So you can see that 2 plus half and 2 minus the 2 plus half, these two will go away. So you don't have to compute the denominator. You know that that's going to be a 0. 0 equals 1 minus 1 over c squared. You now have to solve for c squared. So 1 over c squared equals 1.
implies C squared equals which involves
C is plus or minus 1, isn't it? Because if you take the square root, it's a plus or minus 1. But you'll have to choose one of them because you know this interval is from half to 2. So a minus 1 will not work here. So this implies C must be equal to 1 since C equals negative 1 is outside the closed interval. Okay. Now sometimes you can accept both values provided they both were in the closed interval. Okay. And you found out probably. How about this? I'm sorry, it's pretty small, but let me read it for you. What is the value of C in the interval 16 to 36, guaranteed by the mean value theorem for the function s of x equals 6 square root of x minus 6? Let me write that out here for you. S of x is 6 square root of x minus 6. And the interval given to us is 16 to 36. So you have, again, look at the way it's written. Find the value of C in the interval 16 to 36, but it is not closed interval. But shouldn't it be closed interval for mean value theorem to even work? Yes, actually it is. It's indirectly understood to be closed interval because they're asking us to find the value of C, which is considered as the interior point of the closed interval. Therefore, I come back here and I fix this. But then I will also make observation and I say this one is continuous on this closed interval and it's differentiable on the open interval 16 to 36, which means it's the interior. So C is in this interval, and therefore it's justified as to why they did not give it as a closed interval. All right, now it's time for us to use MVT. So let me write S of x to be 6 square root of x minus 6. And S prime of x. It's 6 x power half, right? So 6 times half x power negative half. That's the derivative that you get, which is 3 over square root of x. Again, I've skipped a step or two so that you'll have the chance to work it out yourself. So that's your function and the derivative. We need S of 36. S of 36 will be 6 times square root of 36 minus 6, which is 6 times 6 minus 6. 36 minus 6, which is 30. And S of 16, the other end, (24 minus 6, which is 18. Then if you come over here, S prime of C is 3 over square root of C. MVT implies, oh no, there's no F, it's in S. So S of 36 minus S of 16 over 36 minus 16 equals S prime of C. See, what we did for F, we're just rewriting it in terms of S. So we have 30 minus 18 over 36 minus 16, which is equal to 3 over root C. So that gives us 12 over 20 equals 3 over root C. Cross multiply and simplify it. So you get root C is 20 times 3 over 12. And if you simplify that further, you get root C equals 5. So square both sides. So you get C equals 5 squared, which is 25. And so that is your, that's your value here. Here's our last problem. A ball is launched from an initial height of 576 feet The height of the ball at time t seconds is given by this equation. Find the time t guaranteed by the mean value theorem when the instantaneous velocity of the ball is equal to the average velocity during its trajectory. I want to first write h of t so you can see it more clearly. So t here represents the time in seconds and h is the height of the ball at any given time t. Now this ball is launched from a certain height and that's the trajectory it follows, right? So if we were to draw this on a graph, it's projected or it's launched from a certain height and it's a parabola, but you're only choosing this portion of the parabola. Again, draw it only up to the ground. Yeah, so it reaches the ground. So technically this goes all the way here, this goes all the way down. So you have the parabola that opens downwards, but remember that this is a practical situation where so it cannot go outside these boundaries. In other words, this is time t and this is h of t, and the time has to be between in positive values, right? So it has to start at 0 and the height has to at one point return to the ground where the height is 0, so it can't go below the ground, meaning you can't have negative height. So no negative t, no negative h of t, the height, isn't it? Now, since we can't have a negative t or a negative height, and also that it was launched at a certain height, it says 576 feet. We know that we want a closed interval for this consideration of the red graph. And so I need to find this time t. And if I can find this time t where it ends, then I can consider that closed interval. So I need a closed interval 0 to 2. And in order to determine that t, I need to understand that that t will happen when the ball returns to the ground. So as a ball returns to the ground implies that the height of the ball is now 0 because it's on the ground. This helps me to determine the time. So I set up the given quadratic equation equal to 0. Use your quadratic formula, the x method or the BC method, and factor out the GCF, which is negative 16. And when you do the factorizing, you get t plus 4 times t minus 9 equals 0. When you set each factor to 0, we get t equals negative 4 or t equals 9. We already established that time cannot be negative, both practically as well as, algebraically here we can't accept it. And that makes it t equals 9. So this t here will be actually 9. So then our interval, so then our given function is negative 16t squared plus 80t plus 576 over the closed interval 0 to 9. Now, if you look at the red graph in between, you can clearly see that you do have, if you connected the 576 and the 9 together, then that secant line, its slope will be the same as the slope of this other parallel line passing through that particular point C. And that's the C we're supposed to find, where the slope of the secant line and the slope of the tangent line will be the same. In this particular instance, the question doesn't call it the secant line and the tangent line because it's a word problem. So here they're talking about the secant line. Let me write that here. The secant line is known as the average velocity, and the tangent line is known as the instantaneous velocity at C. You can say that this is continuous and it's differentiable on the closed on the open interval 0 to 9, the interior of 0. So this implies MVT will kick in now, MVT says h of 9 minus h of 0 over 9 minus 0 must be equal to h prime of c. And as I just mentioned previously, this is the average velocity over this interval 0 to 9 seconds. And this is the instantaneous velocity at time c, when time is c seconds. H of t is negative 16t squared plus 80t plus 576. If we took its derivative, that will be negative 16 times 2, 32t plus 80. And h of 9, you can look at this two ways. One is to first algebraically plug in for t as 9 and compute it. Or you can come back to what we just discovered. We said t will be 9 when height is 0, meaning h is 0. So h of 9 should be 0. And then h of 0, again, you can compute it quite quickly because it's 0 algebraically. Or you can come back to the problem and see, well, a ball is launched from an initial height of 576, which means at time 0, the ball was sitting at a height of 576 from where it was launched. So we have 576 here. H prime of c is negative 32c plus 80. So MVT says 0 minus 576 over 9 minus 0 equals negative 32c plus 80. That gives us negative 576 over 9 equals negative 32c plus 80. So I want you to solve for c here. Clean it up. So you get c equals 4.5. Of course, it should be positive. Now, because it's a word problem, you have to interpret this. So at 4.5 seconds, after launching, of course, then pull the sentence right from the question and say, the instantaneous velocity of the ball is equal to the average velocity during its trajectory. The end. So we've come to the end of this lecture. I hope you enjoyed it. Mean value theorem is super important. And make sure that you check the premise before you apply the MVT on the guarantee it provides. I will see you in the next video. Thank you, Klaus.